So to describe non-dilute mixtures, we could either take the activity approach or the excess property approach. Let's first talk about the activity approach. Okay. All right, and so when we say that we're looking at the activity of a mixture, essentially what we're going to do is we're going to take our chemical potential as species I. That's a function of temperature, pressure, and composition. So once again, this bracketed x just means a set of different mole fractions. In any case, so our chemical potential is going to be equal to the standard state chemical potential at some temperature, and then it's going to be added onto it an RT ln of A sub I, okay, where this A sub I is what we're going to call the activity of species I relative to the standard state, where this is the standard state chemical potential. Okay. Mathematically, this activity, this A sub I, if you rearranged this equation, the activity would just be equal to the exponential of mu I minus mu I naught divided by RT. Okay. All right, and so we sort of actually used this activity approach already, even when we were talking about dilute solutions. Because, for instance, if you consider when we talked about the ideal gas mixture, we said that mu sub I was equal to some molar Gibbs energy of species I plus RT ln of Pi over Pref. Okay? Alright, so that's the equation that we used for ideal gas mixtures before. But this also basically has the same form as the activity method. And so our GI ideal gas at reference is just the standard state chemical potential. And this Pi over Pref is what we would call the activity. So the activity here is Pi over Pref, or if we expand out the partial pressure, it'd be total pressure over the reference pressure times Yi, the mole fraction in the gas mixture. So that was for the ideal gas mixture. But we could also look at when we talked about Henry's law. For Henry's law, we had the chemical potential of the liquid was equal to the chemical potential in the vapor phase plus RT ln of HI XI over Pref. And so here our activity would be equal to HI over Pref times Xi, the mole fraction of the gas in the liquid. Okay? And so generally, when we talk about activity, it's going to be a function of composition, so a function of Xi. At the limit where Xi is very close to 0, or very small, so the dilute limit, we see that our activity is going to be proportional to the mole fraction. Okay, so this is the dilute condition. And this is sort of what we already see in Henry's law, right? Henry's law, we had activity is equal to HI over Pref times Xi. So AI is proportional to Xi, and the proportionality constant is this HI over Pref. Okay. All right, so that's what the activity is in the dilute condition. On the other end of the spectrum, where Xi approaches 1, we see that the activity is about equal to 1. And so we call this the pure limit. And that makes sense, because if we go back to just the base definition of activity, if in the pure limit activity is basically equal to 1, here we would get ln of 1, which is just 0. And so this term would go away, and we would get that the chemical potential of species I is basically the chemical potential of the pure species. Okay? All right, and so the activity approach basically just kind of recasts the chemical potential equations we were using before in terms of activity. And this activity is directly related to the mole fraction.